Welcome to Lecture 3 of Module 3. During this lecture, I will give you an introduction to epidemiological analytical methods that you can use for source tracking of foodborne diseases. You divide these epidemiological methods into descriptive studies and analytical studies. The descriptive studies are, as indicated in the name, studies where you describe a disease situation. You work with often typical two outcomes, prevalence and incidence. A prevalence is a cross-sectional measure, like at this moment in time, how many have a certain disease. So for instance, how many of you would have a runny nose by now? You can also measure over time. So how many of you have a runny nose in the last 2 weeks? That will be an incidence. And more usual, when we talk about foodborne diseases, we measure over a year. So how many cases would there be of acute gastroenteritis in a particular country in, for instance, 2013? That would also be an incidence. Descriptive studies do also focus on characterizing who, when, where, and what. So we want to know something about the cases involved, the age, the gender, the geography, the food consumption habits, maybe if they have some underlying disease, and all these kind of things. And we also want to describe and identify the pathogen and possible sources of a foodborne infection. The analytical studies are more mathematical focused or statistical oriented. They're used to test hypotheses for risk factors and sources. And there are two commonly used designs, the cohort study and the case control studies. Common for both of them are that they analyze the relationship between an outcome and an exposure. So it could, for instance, be a relationship between a runny nose and age, or it could be the relationship between having a diarrheal infection in some country and the relation with the exposure to different foodstuffs. So we are trying to analyze the relationship between certain exposures and the disease in question. So when do we use a cohort and when do we use a case control study? A cohort is, per definition, a study where you are able to actually define a cohort. And a cohort is a group of people that are related by a common event or by something else than the presence of disease. It could be people that have been attending a wedding ceremony and all got sick during this, or not all, but a proportion of these people got sick. It could also be people going to the canteen in a particular school where also, again, a fraction of these people get sick. So you define the cohort, and after that you collect information about disease and exposure factors and analyze if there are some of the exposures that are more common between those that got ill than those that did not get ill. This type of methods are particularly used in the investigation of point source outbreak, where we have like those people that got sick very close to each other and probably got infected or exposed through the same meal of food at the same day. Case control studies are used when you are not able to define a cohort. And here you identify first cases that have the disease, and then you select controls, healthy controls, that is controls that did not have the same disease. And then you identify factors associated with the disease. These studies are particularly used to identify sources of continuous outbreaks and also sporadic cases, and both risk factors and sources. So cohort studies can be divided into prospective and retrospective studies. The prospective studies, there the direction of the investigation go like this way, follows the time. These are not very often used in foodborne infections because we don't sit around, we don't like identify a cohort and then sit around waiting for cases to appear. But just to give you the idea, we have a population. We can follow a population over time. We find out who is exposed, who is not exposed. And then afterwards, we find out among the exposed how many developed the disease and how many did not, and the same within the not exposed. In the retrospective, the direction of the investigation is opposite the time, you could say, because here the incident might already have occurred, or it has occurred already. So you have a definition of the cohort, and then you ask within the cohort, you find out whether people have been exposed or not exposed to particular risk factors or food exposures, and then you, among those that has been exposed, again ask them whether they have been ill or not ill. And this is the method that are primarily used when tracking sources of foodborne infection. For the case control study, you could say that the direction is always against time. So you have some kind of population you want to investigate something about risk factors for. And in the population, you first identify cases, and then you identify healthy controls. And then after that, you find out who have been exposed and who have not been exposed, respectively, for cases and control, and then you analyze the results. Use of analytical studies in outbreaks is very common, and it's particularly useful, of course, if you do not have an identified pathogen, because you will not be helped by using microbiological methods. Analytical studies can also help identify target for microbiological examinations. So if the studies point at a particular food source, it can support microbiological examination. So try to validate, you could say, verify a certain microbiological examination. It's also useful if we don't have any food specimens available. Often in an outbreak situation, the food will be eaten or been thrown away, so you have no way of making a microbiological analysis. It can also be that the outbreak strain is very common, so it's found in other food and sources as well. We can also be in a situation where lab methods are not available that are good enough for detection of the pathogen, or we can even suspect that the lab method has a lack of sensitivity, maybe because to a low content of pathogens in the food, and therefore results are false negative. Often we will use a combination of microbiological methods and analytical studies. There are, of course, a lot of limitations also in these analytical studies. I think one of the worst, you could say, is if we do not have an hypothesis about the source, because then we can ask about 100 to 1,000 different exposures, and that will be very cumbersome and laborious, and people will not remember all these things, and they will not be able to answer all these questions in a efficient way. So in order to use this study, you will need to have some kind of hypothesis. What are you looking for? Another thing is that if the exposure is common, it can be a problem. It sounds a little bit weird, but it's actually true, because, for instance, let's say that it's pork in general, pork meat in general, that is the source of an outbreak. Then both cases and control will actually have eaten this. But the thing is that the cases will probably have eaten it from a contaminated batch, whereas the controls would not have eaten it from a contaminated batch. But you will still have in your questionnaire and in your data set, you will have cases and control listed as had eaten pork, and you will not see a significant difference. There's a lot of other issues here that you can see when everyone is ill. Obviously, you will not have any controls as such. If you have multiple exposure pathways, can also be tricky. If people get the meal served on plates, so everybody would have eaten of everything from the plate, it can be difficult to disentangle the source. If behavioral factors are important, if the study is conducted late in the outbreak, which will both be a limiting factor for people to remember what they have eaten, maybe, but it will also be that there could be secondary cases where humans have infected each other. So the same pathogen will not have the same source, because some will be infected by other humans. And then if the attention from the media is high, if it has been out in the press that there has been some suspected source, then people tend to focus on that source, even if it is not really the original source. Use of analytical study in sporadic infection. Well, first of all, we can use them to identify risk factors. That is not only food exposures, but also other risk factors like predisposing factors. It can be genetics. It could be chronic disease, for instance. It can also be risky behaviors. In many chronic diseases, smoking is also a risk factor, for instance. We can also identify risk-reducing factors or protective factors. So analytical studies for sporadic infection is not only used to identify food sources, but also to increase our understanding of the disease etiology and the epidemiology of the infection. Again, some limitation of analytical study, and this is really a research area in itself. So I will only mention them here, and then you can read further in the suggested literature. But there are some limitation on extrapolating results of analytical studies to the general population. There's this question about having very extensive questionnaires, and in all the complex of the data analysis of the data sets are not always straightforward. A little bit about how we analyze cohort study. For those of you that don't really know where the word cohort came from, it's actually 1/10 of a Roman legion. So that's the definition of the cohort. You have a presentation here of cohort data. It's of course a very simple example, but it's often very illustrative to put it in these 2x2 tables. So in this table, we will have 8 people that has been ill and exposed to a certain factor. We will have 8 people here that are not ill and also exposed, and 5 that are ill, not exposed, and not ill and not exposed. So we can then calculate the attack rate. The attack rate is simply the number of exposed out, the number of ill out of the total number of exposed, and the attack rate for the not exposed are the number of ill of the total number of exposed. And these two rates you can divide and get the relative risk, which in this situation is 1.6. A risk of 1.6 suggests that this is a risk factor, particularly if it's also statistically significant. So if you have a relative risk that is above 1 and statistically significant, it's a risk factor. If it's below 1 and statistically significant from 1, it's a risk-reducing factor. And if it's just around 1, then it's neither. You will probably, when you read through literature, find all these different names: relative risk, risk ratio, rate ratio, but it's actually the same, just so you know. You can be in a situation where you cannot define a cohort, where the outcome is very rare. You anticipate loss to follow-up. There is no time to wait for outcomes to occur. That could also be if it's unethical to wait for outcomes to occur if it's a very serious disease. And in that situation, you can do a case control study. So here we have some cases that are identified from the population, and they are compared with healthy controls regarding past exposures. Controls should obviously be free of disease. That's why they are controls. They should be identified from the same population as the cases, and they should be representative of the study population. And to ensure representativeness, you can do matching. That means that you can select a case with a certain age, a certain gender, living in a certain geographical area, and then you can try to select controls with the similar characteristics. And obviously, the methods for data collection should also be the same. They should be interviewed using the same structured questionnaire, so there will not be any bias in how data are collected. Again, we can present case control data in a 2x2 table, but here it's important that the direction of analysis is in the other way. We will not be able to estimate attack rates or incident rates because we do not have a denominator, because healthy controls are picked and linked to the cases, so to speak. But what we can estimate is the number or the proportion of exposed out of the total number of ill, and again the proportion of exposed out of the total number of healthy controls. And if these differ a lot, if this one is very much higher than this one, then it can indicate that the factor analyzed for is a risk factor. The measure you use here in case control study is called the odds ratios, and it's simply calculated as a cross product. So you simply say in this example 16 times 24 divided by 8 times 24. And then you get an odds ratio of 2. And the interpretation of the odds ratio is the same as the relative risk. Above 1 is a risk factor, below 1 is a risk-reducing factor. From case control studies and cohort studies, you can also calculate something called the population attributable fraction. This is simply where you can go in and you can say the population attributable fraction is the proportional reduction in the population of disease that would occur if the exposure to a risk factor is changed to, for instance, not being a risk factor, not being an exposed factor. So it is reduced to an alternative ideal exposure scenario. So for instance, if you want to check how important is consumption of chicken in Campylobacter, you could go in and say all those that have eaten chicken, let's say they did not have chicken, and how much would you then reduce the population attributable fraction, or how much will you do the number of illnesses. And it's calculated using this formula. So you have the proportion of the population at a current exposure level over here, and you multiply that with the relative risk, and you summarize across a number of exposure levels. In our studies, we will usually only have 2 levels, exposed or not exposed, but there might be other levels if we talk about continuous data. And then you subtract the same, you could say the same measure, but just using an ideal exposure level, and then you divide it again with this measure over here, and that will give you the population attributable fraction. We will come a little bit back to the population attributable fraction when we talk about source attribution, because it is a measure that can be used to, say, give an indication of the relative importance of different food sources when we talk about these epidemiological methods. For further reading, I can suggest that you look into Ringgold's paper on outbreak investigation, and also look into the ECDC, the European Centers of Disease Control's homepage, where they have a whole toolkit for investigating and response to food and waterborne disease outbreaks. There's a lot of good information on that homepage. Thank you very much.